Live from the North Carolina Museum of Natural Sciences in beautiful downtown Raleigh, it's the Science Cafe.
Well, hello, everybody. Yay! Hey! The people who come here a lot don't usually see me get up on stage, but those people know my name is Katie Amman. I am the head of featured programs here at the museum, and this is one of our favorite featured programs, is our Science Cafe, and I welcome to all of you and all of the teachers that are here. You want to raise your hands that you're working with the grant? Hey, it's great to have you here. Yes, we do this every week except for the first week of the month where we have science trivia. And we have science talks here with beer and food. It's fun. So today, our Science Cafe today is inspired because of something that's going to happen this weekend. And on the 26th, it's International Sun Day, and it happens to be on Sunday. And we are going to be having some talks at the museum, and on Sunday afternoon, and you'll be able to come here and look at the sun through our solar telescope on the roof of this building. But we wanted to sort of get you started thinking about the sun, learning about it, and that's why we're having this cafe tonight. And our speaker is the assistant head of the Astronomy and Astrophysics Research Lab upstairs in this building. His research is involved with galaxies, looking at galaxies, and he's going to correct me. We did a little bit of practice before I got up here. But it's how they evolve, their shape, how they act, yes, and black holes and dark matter. So if you have any questions about that, we'll do that after the cafe. But he's here tonight to talk to us about the sun and to help you know all the different parts about it, what it does and what it affects in the universe. So anyway, let's give a warm welcome to Patrick Treuthardt.
All right, thank you. Yeah, so my passion is actually galaxies. So at any, afterwards we can definitely talk about that because I love galaxies. But yeah, so what I'm going to talk about today is about the sun, our closest star, one of about 300 billion stars in our own galaxy, but the one that we know the best. So let's actually talk about that. So the first thing we need to talk about, though, is sun safety. So you never want to stare at the sun. Your eye basically works just like a magnifying glass. So it's basically the light rays from the sun come in parallel. They go through the front lens of your eye, and then they can basically be focused onto the back of your eye. So if you stare at the sun for a long period of time, you can actually burn the back end of your eye, the back side of your eyeball. And you won't feel it either because you have no nerve endings in the back of your eye, so you won't actually know that you're doing damage. So you never really want to stare at the sun for a long period of time. But what you can do, if you do look at the sun, sometimes you get these white spots. Those are okay, but never stare at the sun because then you can end up with actual burns on the back of your eye. So never do that. So there are tons of ways to safely look at the sun. The easiest way is something called a pinhole projector, where it's basically just as it sounds. You just take a piece of paper, you punch a little pinhole in it, and you point it toward the sun, and the light that comes through it'll actually show you an image of the sun on the ground or on another piece of paper. And that's a perfectly easy way to look at the sun. It's a little more expensive ways. There are special made telescopes that you can buy if you want to spend $1,000 or so. You can use binoculars and project an image of the sun onto a piece of paper or something like that using binoculars. You can also use a welding helmet if you happen to have that. And also one of the other really cheap ways is occasionally, like magazines like Sky and Telescope or Astronomy magazine will have these aluminized mylar glasses in them. These basically cheap paper glasses, and you can also get these online. You can get like a bulk of them for, I don't know, $10 or something like that. You can probably get like 50 of them. But they're cheap, but they're actually safe, so you can actually look directly at the sun wearing these glasses. So that's pretty good. But the pinhole projector is really good too. So, oh man, I forgot my prop. So what I wanted to talk about, though, is also the size of the sun. So everybody's familiar with the Daily Planet globe that's outside on Jones Street, just on about halfway down the block right here. If you imagine that as the size of the sun, the relative size of the Earth is basically a soccer ball. So about like that big. So imagine putting that right against the globe. If the globe is the sun, the soccer ball is about the size of the Earth. So the sun is enormous. It makes up about 98% of the mass of the entire solar system. The rest is, it makes up more than that. Sorry, it makes up 99.98% of the mass of the solar system. The rest is planets, and most of that is Jupiter. So the Earth is basically insignificant, mass-wise. So here's an image basically showing you the relative size of the sun. So you can see that's the disk of the sun. You can see the Earth there, and Jupiter, the largest planet in the solar system for relative size. You could fit about 110 Earths across the face of the sun, stack them side by side. So the sun is really massive. It's really big. Here's another awesome picture to show you the scale. So that's the sun in a different filter. And that's a giant magnetic loop with plasma trapped in it, and so you can see the relative size of just this loop compared to the Earth. So the loop itself is bigger than the Earth. So it's pretty fantastic. But then again, the sun is not the largest star that we've ever found either. So what this video is showing is just the relative sizes of different things in the solar system, and then we're going to zoom out and actually show you the different sizes of different stars as well relative to the sun. So here's the Earth, and there's Venus just before it. And I don't know if you can see it now, but Venus is actually rotating opposite, which it actually does. That's pretty cool. Uranus, that actually rotates at about 90 degrees relative to the orbital plane of the solar system. There's Saturn. There's Jupiter, and you can see how much larger it is than the Earth. Here's the sun, to give you a sense of scale. And now we're going to look at other stars. So this is Sirius A. It's one of the brighter stars you can see out in the sky. This is about 1.5 times the size of the sun. Arcturus is about 26 times the size of the sun. Aldebaran is a red giant. That's a pretty big star. Rigel is a blue giant, about 78 times the size of the sun. Betelgeuse, that you can see in Orion, in the upper left corner of Orion, that's a red giant. And then this is the largest star we've seen so far. It actually defies logic. We don't actually know how stars can get that big. But that's the largest star we've seen. And you can see that completely dwarfs anything that we've seen so far. So that's pretty amazing. So, oops. So to give you a sense of where the sun is in our own galaxy, this is an artist's conception of what we think our galaxy looks like. The galaxy is so large that we can't actually get outside of our own galaxy to take this picture. So we have to kind of get creative and figure out what the structure of our own galaxy looks like. And we think this is where we are in our galaxy. So we're about halfway out from the center, not at the end, or not on the outside, not directly in the center. We're about halfway out between two spiral arms, just kind of in a normal, average location. So what is the sun made out of? I'm going to breeze through this pretty quickly. So here's just a picture of the periodic table. The main components of the sun are hydrogen and helium. So the two most common elements in the universe, and the simplest to make. That is basically all the sun is hydrogen and helium. The sun is also made of some other elements, but it's really insignificant. So if you take a little pie chart and you look at what the sun is actually composed of mass-wise, about 75% of it is hydrogen, about 25% is helium, and we're rounding here. And basically, there's a lot of other elements in it, but it's almost insignificant. So it's basically hydrogen and helium, the two most common elements in the universe. All right, so now we're actually going to get at some of the cool stuff with the sun. So this is a cutaway section of what the sun looks like. And you can see that actual surface in this image right here, that surface is what we call the photosphere. So this is the layer of the sun that you can see with your eyes. So when you're seeing the light coming from the sun, this is the photosphere. This is what we call the surface of the sun. Even though it's a giant ball of plasma, like a really hot gas, this is what we actually identify as the surface of the sun. And then there are layers above it as well. There's something called the chromosphere, which is where we see a lot of that magnetic activity, where we saw those giant loops. That's where you see that in the chromosphere. And then above that is something called the corona, which is just like these bright streamers of plasma kind of coming off the surface of the sun. So this is the photosphere. So this is the part that you see every day, and hopefully that we're going to be looking at on Sunday if you guys come by. But if we zoom in on the chromosphere, if we zoom in on the photosphere, what you're going to see, is this playing? Yeah, what you're going to see if you look in really closely, if you zoom in really closely, you're going to see that the surface of the sun actually looks like boiling soup. So if you can actually see this in the videos, I don't know if the yellow one doesn't look like it's playing. The orange one looks a little jumpy, but the yellow one is actually a lot better. But what you're seeing there is basically these cell regions on the surface of the sun, and they're changing with time. It's basically what's happening is hot gas is coming up from inside the sun, reaching the surface, releases a bunch of light and heat, and then it cools down and sinks back down, along those dark edges. So you get the cellular pattern where it actually looks like boiling soup. And so that's what we actually see in the photosphere if you zoom in on it really closely. But if we zoom out, if we just look at the sun more generally, what you can see, depending on the year, you can see a lot of these dark spots on the surface of the sun, on the photosphere. And these things are called sunspots. The reason why they're darker is because they give off less light than the rest of the surface. So the surface of the sun, the photosphere, is about 6,000 degrees Celsius, and these sunspots are about 1,000 degrees or 2,000 degrees cooler than that. So they're still extraordinarily hot, but they're not as hot as the rest of the surface, so they look a little bit darker than the rest of the surface. And as you watch this video, so this is taken over a period of about 12 days or so. And you can see that the sunspots actually change with time. You can see that they start to form and grow and split apart, things like that. So you can see sunspots actually changing with time. So what we do see, so ever since the time of Galileo, so in the 1600s, when basically somebody decided, hey, I'm going to use a telescope and actually look at objects in space, Galileo looked at the sun and saw that it wasn't a perfect sphere. He noticed these blemishes. He noticed these dark spots on there. And ever since that time, people have been looking at these dark spots and counting them. And so we have records from the 1600s all the way up until present day of how many of these sunspots we see every day for years. And what we notice is, from all this data, is that the numbers of sunspots reaches some peak, drops to some minimum, reaches some peak, drops to some minimum, and that cycle happens every 11 years. And as to why that happens, we really don't know. I mean, that's still a really active topic of research. I mean, everything that you see on the sun has something to do with magnetic fields, so it's likely has to do something with that, but we just don't have a really good understanding of how the magnetic field system in the sun works, so that's a really active topic of research. But you can see that, that the cycle happens every 11 years, so you'll hit some maximum number of sunspots one year, and then 5.5 years later, you're going to hit some minimum number of sunspots where you may not see any for a period of days. And then, 5.5 years later, you're going to hit some maximum number again. But you can see in this graph, there, right in the 16 to 1700s there, you could see that there was actually a period where that 11-year cycle, basically you saw nothing for a long period of time, which is actually pretty interesting. Because that actually corresponded, so this is known as the Maunder minimum, and this actually corresponded with the coldest time during a period in history called the Little Ice Age. So, and so during that time in London, the Thames River, so that was an image of the Thames in modern day, but in the late 1600s, the River Thames actually froze over. So we have like oil paintings from the 1600s showing people like ice skating and having winter fairs, things like that during the coldest part of the Little Ice Age. Now, the thing is we don't know exactly, I mean, this is one data point, right? We have one data point where we have very little sunspots, and we had a time where the Earth was relatively cool. Now, that's never happened before, that's never happened since, so there's a correlation there, but there's no evidence to suggest that one thing causes the other, so we have no idea. But it's just interesting that those two things happen at the same time. Now, if we end up having a long period again, like another Maunder minimum, and we have a period of global cooling, that would be interesting. So somehow solar activity may then influence, or the lack of solar activity may actually, cause global cooling, but that's completely unknown. But that would be pretty interesting. So this is the last two solar cycles. So this, on the hump on the right there, that is actually the solar cycle we're in now, and you can see that we're on the downward trend. So we reached the maximum at about 2015, 2014. So we're now on our way down to a minimum. And if you look at this graph, the maximum, the peak there isn't really that high. So we weren't getting a large number of sunspots during that time either. So the cycle right now seems to be pretty low. And just the last week or so, there were 4 days where we saw absolutely no sunspots on the sun. So keep your fingers crossed if you guys are coming on Sunday, so that way we can actually see some sunspots too, because it'll be pretty cool then. All right, so the talk is common and uncommon events on the sun. So solar sunspots are pretty common. The Maunder minimum is really uncommon. One other common thing that we see are solar eclipses. And so this is a video that somebody took in Australia of a solar eclipse. So this is basically when the moon passes between the sun and the earth and blocks out the sun. And then what you're left with is that bright haze around the moon. And that's the corona. That's the uppermost atmosphere of the sun. That's a really good time where you can actually see that for a couple minutes. So this is just a diagram showing you what happens. So you have the sun. Obviously, this is not the scale. So this is the sun on the far left. You have the moon in the middle, and then the earth on the right. And if you're in the darkest part of that shadow, if you're standing on the earth where the darkest part of that shadow is cast onto the earth, then you're going to see that beautiful eclipse like that. And fortunately, next year, August 21st, 2017, we are going to be in an excellent place to actually see this happen. So there's going to be a solar eclipse that's going to pass over the United States. So if you happen to be anywhere in the middle of the United States, from West Coast to East Coast, actually, if you happen to be in Charleston on August 21st, 2017, you're going to be in for a treat for about 2 minutes. You're going to see the sun blocked out. Birds are going to go a little crazy because they don't know what's going on, and then it's going to be over, and then you're going to go about your day again. But it's going to be pretty fantastic. If you get a chance to see that, you definitely should. I think it's in the middle of the afternoon. It's about 2 p.m. is the maximum totality along the East Coast. So you should definitely check that out. And so here's just a zoomed-in view. I don't know if you guys are close to the monitors, you can kind of see where cities are and things like that. But the dark band there is where you can see the absolute total eclipse. If you're along that red line, you're going to get the best show ever. The middle, or the blue line, the line in the middle. But if you're anywhere in that dark band, you're going to see it. You're going to see the sun completely blocked out. So you got some really good choices there. I think Columbia, South Carolina is actually in that too. So you have some really good opportunities. So one other really cool thing that you see with the sun is something called an aurora. And so this is a real-time video in Iceland of the aurora, of the northern lights. This is aurora borealis. And so you see these green lights in the sky. This is actually caused by the sun. And so what's happening is, well, let me let this video go for a little bit. So you can actually see these waves of, look like green ribbons in the sky. I have never actually seen this in real life. This is just beautiful, but I've never actually seen this. But what's happening is, it's due to the charged particles that are being basically strewn out by the sun all the time. So the sun is just a giant ball of plasma. So it's basically nuclei, so it's like atoms and electrons, and they're constantly streaming out from the surface of the sun into space. And sometimes those particles will hit the Earth's magnetic field, and when it does that, some of these particles will actually get trapped in the magnetic field and then spiral down and hit the Earth's atmosphere. And when they hit the Earth's atmosphere, they're going to energize, the nitrogen molecules, the oxygen molecules, things like that, and then it will cause them to glow. And if you get a lot of charged particles, and they're really slamming into the magnetic field, then you're going to get beautiful aurorae like the one we saw there in real time. So that was actually pretty spectacular in Iceland. And this video is just beautiful. This is obviously this is sped up, but these are aurorae seen from the International Space Station. So you can actually see it from top down rather than from bottom up. And yeah, so there you can see there's Europe. And on the horizon there, you can see the aurora. And all those flashing lights, that's all lightning. So yeah, it's just amazing. It's amazing the views they get. So yeah, we'll move on from that. So we also get things that are somewhat common. We get solar eruptions. So we get different, basically, what will happen is gas will, generally kind of burst out from the surface of the sun occasionally. And basically send a large amount of charged particles into space. So what's happening there, the reason why you get these bursts is because you have a lot of magnetic field activity on the sun. And these magnetic fields will get twisted up and they'll get really twisted up. And eventually, the analogy, actually a better analogy that I heard recently from actually a solar physicist was if you imagine taking like one of these long balloons where you're making balloon animals and you keep twisting it up and twisting it up and twisting it up. And eventually, you're adding a bunch of energy to this balloon, right? And as you keep twisting it up, eventually it's just going to pop, and then it's just going to release all that energy, right? And then you're going to get like balloon bits everywhere. And that's basically what's happening with these magnetic fields. They keep getting twisted up until it reaches a point where it can't get twisted up anymore, and it just you get something called magnetic reconnection, where it no longer wants to be attached to that point on the sun, and it tries to, it reconnects to a different point. And when it does that, all this material comes bursting out of the sun and gets flung into space. So that happens more so on the peaks of solar activity, but not so much on the way down. So one interesting thing, this is one of these uncommon events, was back in 1859, there was a British astronomer named Richard Carrington, who was actually just sketching sunspots. So he projected an image of the sun onto a piece of paper. He was just sketching sunspots. And he saw at this time, when he was sketching this specific sunspot, he saw all of a sudden it started getting brighter. And he had no idea what was going on. He called in his assistant, who came in and was looking at it too, and they saw it get brighter and then kind of dim over a period of about 5 minutes. And they had no idea what was going on. Then about 12 hours later, weird things started happening on Earth. They were getting auroras, as far south as Havana, Cuba, and Hawaii, and Rome. The telegraph machines started shorting out, and the wires started burning the paper. So they disconnected them from the batteries, and then they realized that they could actually still send telegraphs without them connected to the batteries. So they really had no idea what was going on at that point. But what we know now is that Richard Carrington actually saw a solar flare, a solar eruption, happen at that exact moment. And it was directed directly towards the Earth. And what we now also know is this is the strongest solar flare event that has been ever happened in probably 500 years. And obviously it was so powerful that there was so much electrical activity in the air that you could actually disconnect electronic devices. There were very few, like the telegraph machine, but they would still work. So this is actually a really rare event. But the thing is what would happen now if a Carrington-style event happened in these days? Now we depend on electronics for pretty much everything, for every day-to-day life. But if we talk about like space things, there's obviously a lot of satellites in orbit. What you're on the far left there, you're seeing basically just a little schematic of like all the known debris and satellites in orbit around the Earth. So there's a lot of stuff up there. You have astronauts in space, you have the space station with people in it, things like that. So they potentially are in danger. The electronics and satellites for sure are in danger. The people, if they can get inside the space station, they should be pretty much okay. But, you don't want to take chances either. But the biggest thing is these satellites, right? So we could lose communication, we could lose GPS signals. And so if you happen to be in a plane that's landing, or a ship that's docking, or in a train that's probably has like heavily obscured views, they rely on GPS to pinpoint their exact location. So when you run into dangerous situations, if you happen to be on one of these things, it could be bad news. So so you kind of don't want to be there when that happens. And so something more minor than the Carrington event actually has happened in 1989. There was a flare event that was much less severe, that impacted the Earth and actually knocked out power transformers in Quebec, Canada, and New Jersey. So Quebec actually lost power for about 9 hours. And so these transformers actually melted. There was so much electrical activity into the power grid that it actually melted the power transformers. And so you can see in the upper right corner, you can see what a power transformer actually looks like. In the bottom right corner, you can see what a melted one looks like. And that's a power transformer in New Jersey that melted down in 1989. And so this is a plot I found recently on the NASA website that shows our power consumption versus how much transmission lines we actually have. And you can see that our power consumption is actually more than what we can actually handle. So the problem is now if a Carrington-style event happens, like it's surely going to fry some things. So we're probably going to lose power for a while. And the estimated cost for one of those, to replace all that, is going to be about $2 trillion. And it's going to be a while because they have to refabricate a bunch of power transformers and install those. So if a Carrington-style event happens, we're going to be without power for a little while. So you want to be careful. So anyway, so it's basically, I don't want to leave it, I'm sorry that I'm leaving it on such a down note, but we'll leave it at that, and hopefully we'll have some good questions and nobody will cry. So
thank you, Patrick. Let's give Patrick a hand. So those of you that are new to cafes, it's all about your questions at this point. And so I have a mic, and Roy has a mic, and it's really important that you ask your question in the mic so everybody can hear it. And we'll get started.
Okay.
So I'll let you go.
Does the sun rotate?
It does. It rotates about once every 24 days. And so, and you can measure this. You can measure this on your own if you wanted to. If you project the sun and there happen to be sunspots, if you track a sunspot, you can watch it as days. If you want to do this experiment at home, you get binoculars, you project the sun onto a piece of paper, and you sketch where the sunspot. You sketch the edge of the sun. You sketch where the sunspot is. And then the next day you look at it again and you sketch where the sunspot is, and you can keep doing that as the sunspot rotates around the surface of the sun, and you'll see that it takes 12 days to go from edge to edge, and you multiply that by 2 because it has to go back around the other side, and it's 24 days.
Just need to get on camera.
So that's the easy way of measuring it.
Yeah, right.
Yeah.
So I apologize, this isn't about the sun.
Oh, that's fine.
But when Katie introduced you, she was talking about your interest in galaxies.
Oh, yeah.
And she used the word evolve.
Yes.
That galaxies evolve. And so it got me thinking whether there is a kind of natural selection in the population of galaxies, because they are born,
Right.
and they die, and maybe, on a very prolonged,
Right.
time frame, but perhaps they die not randomly, but according to some fitness with the galactic environment.
That's actually pretty true. That actually works. So there are two main types of galaxies in the universe. There are elliptical galaxies, which basically look like footballs or hoagie buns. They're just balls of stars that are kind of randomly, stars kind of randomly strewn everywhere. And then you have spiral galaxies like the Milky Way picture I showed you, where they just look like pinwheels, and they're very flat disks. The elliptical galaxies do not have new stars forming. So all those stars are old, and they'll just fizzle out and burn out eventually, and then you'll just be left with a dark clump of mass. The spiral galaxies have ongoing star formation right now because they have dust and gas in them, and that dust and gas will collide and form new stars. Now, eventually, that dust and gas is going to run out. That fuel is going to run out, and then you're going to end up with, a red and dead galaxy. But if you can feed a galaxy more gas, you can have ongoing star formation. And so there are galaxies that, do get kind of fed occasionally gas that will kind of reignite star formation. And so those galaxies will actually be around longer than, for instance, and when we talk about this, we're talking about like the length of lives of the stars that make them up. But yeah, but eventually, those spiral galaxies that can continuously be fed gas, those will actually last longer than the elliptical galaxies that won't have gas. Yeah. So in a way, yes, there's some selection to that, I guess. Yeah.
This is a practical question. Can you use two polarized lenses from polarized sunglasses, turn them at 90 degrees and look at the sun?
If you turn 90 degrees, you're not going to see anything. But you don't know. Actually, polarized glasses are terrible. You should never use those, because what it's doing is, and this is actually the worst. If you have polarized sunglasses that do not have UV filters on them, you should throw those out, because what's happening is it's actually, so you're getting in half the amount of light, but without the UV filter, your pupils open up. And when it does that, more UV light is coming into your eye, and that'll actually give you cataracts. So don't do that. So if you have polarized glasses, make sure that it has that UV coating on it. Otherwise, you're just doing more damage to your eyes. So yeah, make sure you have that UV coating on polarized glasses. Oh, yeah.
The sunspots, did they have anything to do with the Great Blackout on the East Coast in the 60s?
Oh, in the 60s?
Yeah.
That I don't know. So the thing, okay, I don't know about that event particularly, but when you see sunspots, that means solar activity. So when you have solar activity, you have sunspots, you have those loops that we saw, you get the solar flares, you get all kinds of stuff happening. So when we looked at that cycle of 11 years, when we looked at the sunspot number, when it reaches that peak, I mean, there's a large number, there's usually a large number of sunspots every day, and that means there's going to be a lot of solar activity. So those are the times of year, or those are the years where you can expect to see a lot of solar flares and potentially, things happening to satellites and maybe power grids, things like that. But that specific event, I don't know. Yeah.
Over here.
Yeah.
Why did you choose to be an astrophysicist?
So that's the best question. Because I'm a big nerd. No, I love, all right, so the path I took was, when I was a kid, I just loved science to begin with. And my mom would get Discover magazine, and I would just kind of flip through it. And I love dinosaurs, I love ants, and I love space. And so I was, and then when I got into high school, I took like biology and things like that, and biology was just memorization, and I didn't like that. And then I took physics. Well, I took chemistry, that was cool because there was more math in it. And then physics, I took physics, and that was basically using math to explain how things work. Like how things move, how things behave, things like that, and it was great. And then I realized that astronomy is just physics in space. So you can use math to figure out how things are working in space, which is the best, because the space has the coolest things, like black holes, dark matter, things like that, so galaxies. So, yeah.
Yeah, I have a question about the aurora. Do scientists know why it's always green versus being another color?
So I think it is other colors too, but not as frequently as green. So you can see red. I think you see purple. But it's mostly green because nitrogen makes up most of the atmosphere, and so I think I think the solar particles, the charged particles are impacting mostly nitrogen, and nitrogen will glow green. But I don't know for sure, but I think oxygen kind of gives you that pinkish glow, but I'm not totally sure about that. Yeah, is that okay? I have agreement right here.
Yeah, I only knew about argon. Like argon lasers are green and blue, but.
Yeah, well, I mean, there are a lot of, so the thing is, too, there are a lot of electrons in all these atoms, and really what it has to do with, like, electron placement and them getting energized and then kicking back down and then glowing and things like that. So there's a lot of stuff going on, but yeah, I mean, argon, when you have, like, the argon lasers, right, they're specifically trying to get out, they're kicking electrons up to this energy level and then letting them drop back down so they'll emit this light. And they want that specific green light, and that's exactly what they're trying to get. So, yeah.
Well, it may be that's why your eyes are attuned to see green as like the peak sensitivity for green. Maybe that's why it's more noticeable.
Well, that too. Yeah. It's that's true, and I'm not totally sure if it's just the green lasers are brighter too. I don't know, but yeah, your eyes are definitely attuned to green more. Yeah.
Do the galaxies all, or most of them, rotate in the same direction, same plane?
So, that's a tricky question. So, I wish I had a really cool animation for this. So the thing is, the way galaxies, very few galaxies are just on their own. Galaxies tend to be in groups, and those groups tend to be in clusters. So you tend to have galaxies in giant gravitationally bound systems, and those systems all lie in the same regions as a lot of dark matter in the universe. And what you'll see when you zoom out and you look at the universe as a whole, like just really broad spectrum looking at the universe as a whole, what you see is that the universe actually has like a spongy structure. And what I mean by that is there tend to be filaments where you find a lot of mass that you can see. So like dark matter, well, that you can see is like dark matter and then luminous matter, things like that. But then there are also voids where there's pretty much nothing. So it just looks like a sponge that you cut in half, right? So you can see like all the filaments in there, but then there are empty pockets in there too. And so when you look at galaxies that are along these filaments, they are not completely randomly oriented. They do tend to lie along these filaments, although it's not a strong correlation. It's very, very weak. But there is a slight correlation to the orientation along these filaments. Yeah.
Hey,
Hey, Patrick. It's a citizen science question.
Okay.
Probably should have asked you ahead of time.
Nah.
But basically, we have a bunch of 40 teachers here from around the state who are being trained by our by teachers who have been working with us on the Students Discover project, and they're coming here to learn about how to do citizen science in their classrooms. So let's hear it for the teachers who are here. Who are you? Woo! So they're all doing awesome citizen science projects that we've been working on as scientists here in the museum, but we're not currently doing any citizen science projects that are related to physics or astronomy. And so I was wondering if you knew if there were any projects in CitSci that are more in that realm that you might want to bring to their attention, because I'm sure they're really interested.
Yeah, so so the problem is, like, astronomy is heavily computer based. So there's very little really hands-on things that you can do, but there are some cool things that you can do. So computer-based stuff, there's the Zooniverse, for instance. So you can go online, you can look at Galaxy Zoo, which I'm going to plug because that's the best. But you can go in Galaxy Zoo, and basically it'll train you really quickly and show you how to classify galaxies, and then so you can add classifications to galaxies that basically, some people have never looked at, or maybe 2 people have looked at out of a catalog of millions and millions of galaxies. So you can help classify those, and some papers have already been published using citizen science classifications, and those papers are pretty phenomenal. There's the trends that we're finding in large number statistics of galaxies is great. So other things that you can do that are kind of astronomy related, there are dark sky projects where you can, this may cost a little bit money, but I also have an idea that I want to try. So I'm not gonna say more about that. But I have an idea. Well, there's a way that you can go out and basically measure night sky brightness in different areas. And generally people use I don't know, like light meters, right? So they go out with light meters. They measure the night sky brightness, wherever they are, wherever they happen to be, in the middle of downtown, in the middle of a rural area, something like that. And then they send that data to a website, and then that kind of aggregates it and shows you what the dark sky brightness is. And that's actually good for not only for astronomy but also for biology, right? So you're seeing, so you can track trends of brightening of night sky and how that affects like animal behavior and human sleep patterns and things like that. And the other thing, the more obscure thing that is cool, is if you have money and you want to buy 2 telescopes, what you do is you track the moon. You basically have a video of the moon using 2 telescopes, and you can watch things impact on the moon. And if you do that, you can actually, so NASA has an ongoing project where they're tracking impacts on the moon. And the way you can track it is basically when something of a minimum mass impacts the moon, it creates a flash of light. And so you can actually see these flashes of light. And so by doing that, NASA's basically trying to figure out the masses of things that are impacting the moon, how frequent it is, things like that. Because if we ever want to build a moon base, we need to know basically if people are going to be safe on the moon, or do they need to really dig far down, and how far down do they need to dig so they don't get impacted by a meteorite. But that's actually a really cool project. And the reason why you need 2 telescopes is because there are cosmic rays, or basically these really energetic charged particles, and they'll pass into the camera of a telescope. But basically you won't, if you have two cameras on 2 different telescopes, you won't have the same cosmic ray hitting both telescopes. So if you see a flash of light in one and you don't see it in the other, that means it's a cosmic ray. If you see the same flash of light in both telescopes, that's probably an impact on the moon. So, yeah.
Patrick, how long have humans been sort of tracking and studying the sun, and what sort of things have sort of amazed you that the ancients might have done in that study? Yeah, so astronomy is the oldest science. So they've been tracking the sun since since the time of the ancient Greeks. I mean, that's when they've been. I mean, they've been doing it before that, but they have been the reason why we always focus on the Greeks and not like the Arab cultures and the Chinese cultures and things like that is because the Greeks, it's my understanding, the Greeks were in it purely for understanding how it works. The other cultures, my understanding is that they were more interested in how it related to astrology, which is not a real science, and
and farming and how that affects their daily lives and things like that. The changing of the seasons. So people have been recording things for a long time, and so some of the coolest records that we have in the United States, in New Mexico or Arizona, I can't remember now. I think it's New Mexico. There's actually a cave painting of a supernova event in 1054 AD. And they actually recorded, well, we're pretty confident that they recorded the supernova event. So you can actually see, they showed basically a star getting brighter in the sky, and then it faded away, and they actually drew that. And there's recordings of that in China. There are no recordings in Europe, I think, but there are reasons for that.
Raining.
Yeah, it was raining the entire time. No, I think, honestly, from what I've read, I think it's because of political reasons that it was suppressed. So for religious political reasons at that time. But yeah, so there's it's actually, there's a lot of record of ancient things. So it's pretty cool. And there's also the Ankathera device, or I think I'm pronouncing it wrong, but there's this device that they found on a sunken Greek ship that they had no idea what it was, but now they've recently kind of figured out that it was a teaching tool for predicting where things are in the solar system, and predicting solar eclipses and things like that. It's pretty cool. It's pretty amazing.
That leads to my question. Is there any predictability to these things that you're talking about, like the aurora or even flares or? Yeah, so the mechanical things are easy to predict. So like solar eclipses and things like that, those are easy to predict. The way the sun behaves is harder to predict because we don't understand it well enough. We don't understand how it we don't understand the inner workings of the sun. We don't know how the dynamo works to create all these magnetic fields. So predicting when solar flares will happen is basically you can't do it. We know from the 11-year cycle when we can expect things, within a period of years when we can expect more things to happen. But we can never predict, okay, this is going to be a major solar flare, it's going to happen, and it's going to be directed toward Mercury, or this one's going to be directed toward Earth. There's no way we're going to predict that in our lifetime for sure. So that's totally connected to the aurora? Like if I want to see aurora,
right,
and I'm going to take a vacation, is there any way to?
Right, so what you need to do is, so there are plenty of, NOAA, the National Oceanic and Administration, Atmospheric Administration, they track solar activity, and when there is like a lot of solar activity, and other, so they track it, and other websites kind of aggregate that information and stuff, and there are places where there are websites that will show you. There's a good website called spaceweather.com that will actually show you the auroral oval. So it'll show you where you can expect to see a lot of auroral activity in the northern hemisphere. And that oval will get bigger if there's more solar activity, and it'll shrink if there's less. So you can have a period of a day, where you can say, okay, yeah, there was a lot, there's a major solar flare event. It's happening. It's coming towards Earth. Go to Alaska, and maybe you'll see something. Yeah, yeah.
Are there any ancient Chinese or Greek or Arab records of extraordinary aurora extending south that we might assume are something equivalent to a Carrington event?
That's a good question. I am not aware of any. I don't know. Although I have not really looked into it, though, either. It could be. I would assume... It's weird. Well, okay, 1850s, yeah. I don't know. I don't know about that. That's a good question. I actually want to look into that. I don't know. Yeah. Okay.
Okay, so, does the okay.
You gotta do it. You have to.
Well, it is going on the internet, so you have to.
Our galaxy, is it revolving? Okay, so you know how the planets revolve around the sun.
Right.
Does our galaxy revolve around
a common center? So the center of the stars in the galaxy rotate around a common center.
revolving around something else? Do we know?
Not really. I mean, it's not just free floating in space, but our galaxy is in part of a group called the local group. So there's a bunch of galaxies that are all bound together by gravity. And so there's a common, what we call center of mass. So they're all bound together by gravity. And so like if one strays too far out, if one gets some speed, strays too far out, it's still going to be bound by gravity and it's going to fall back in toward the other ones. And so you can just imagine them kind of getting scattered in all directions. But so they kind of move around, let's say, a common center of mass, and that center of mass is kind of moving through space. But they're all kind of scattered around that. Yeah.
Okay. Go ahead.
Can I ask about gravitational waves?
Sure.
What kind of impact does the detection of gravitational waves have on the things that we can learn about our galaxy?
So the cool thing is gravitational waves are opening up like a new frontier in astronomy. That basically we're going to be able to use that if you know we're just getting started with this. But as we develop, as we get more gravitational wave detectors up, as we get bigger ones, we're going to be able to peer further back in time than we have been able to so far. So right now we basically just use light to see as far back as we can, and we reach a wall or we can't see anymore. But with gravitational waves, you're going to actually be able to look beyond that. If it's basically if you up the technology, so that's going to be really cool. Because right now we can only see as far back as 300,000 to 400,000 years after the Big Bang, which is a really short amount of time. But there's a firewall there that we just won't be able to use like normal light with. But gravitational waves we're going to be able to use. We'll be able to peer beyond that. But also, I mean, so it's telling us about. So right now, it's actually what we have. What those physicists have done now is that they basically have shown that black holes will merge, and it seems to happen pretty often. So they've actually had 2 detections of 2 black holes spiraling into each other, and they've got those detections within a couple of months of each other. So it's pretty amazing. So it does happen. It seems to happen frequently. I mean, we have 2 data points, but the fact that they're so close together, it's kind of cool. I mean, if we get more data points, those 2 may be outliers, but it's pretty neat. Yeah.
So you said that another huge solar flare could possibly burn out power through a large area. So if they could detect it in time, would they have about 12 hours to shut down all the power and save them from that?
Yeah. Yeah, they would have. Well, depending. I mean, if it's that massive, it actually. Yeah, it moves pretty. It'll move pretty quick. I mean, it's not going to be like minutes, but yeah, you're going to have hours to do that. So, I mean, I don't know how the electrical system works, but yeah, if you can disconnect everything, like everywhere, then maybe you could save it. You may have some like fried power lines, which may be easier to replace, but then you may not damage, really hard to manufacture things like power transformers and things like that. But then again, also if you're on a home battery system, like what Elon Musk is coming up with these ideas for these lithium-ion home batteries, where basically you just store your own electricity. You use a solar cell, you gather your own electricity, and then you use a battery at night. So you're completely off the grid. That would actually save a lot of headache, because we're not relying on a single place for all of our electricity. Now it's just basically spread out to everybody. Everybody has their own electricity. So now it doesn't tax the overall grid system as much. So yeah.
Is there any astronomy that we can do during the day? The pinhole camera of the sun is a great example.
Yeah.
Other things we could do during the day?
That you can do. Well, okay. Solar astronomy is going to be the easiest, but you can do. Are you one of the teachers? Okay. So some of the cool things you can do with students is if you have like a semester to do it, you can actually have them track. Where the sun is in the sky and watch how the seasons go. So one thing you can do, and this is really simple, is you just have like a piece of wood or cardboard or something like that. You punch a pencil through it, whatever, and you have a really sharp pencil. And then every day at noon, on the same piece, like you don't move that piece of paper. Every day at noon, you draw where the tip of the pencil is, and then you write the date. And you do that every day for months, and you can watch how the sun at noon basically gets lower and lower in the sky from summer solstice to winter solstice, and back and forth. and you can see where noon is. You can see how it changes, how the angle changes during the year. So basically, you're looking at the movement of the Earth around the sun, and because the Earth's axis is tilted, so it's all kinds of stuff. Telescope-wise, sunspots. If you can project the sun, just have them track sunspots. That's actually really cool to see. So if you can do that over a period of 12 days, you can definitely. That's a really easy project to do. You just have them draw sunspots every day. Just trace them out, and you can see how the sunspots change and how they move. So it's cool.
Patrick?
Yeah.
So there's a big population in the northern hemisphere, and we have the aurora borealis.
Yep.
Low population in the southern hemisphere, the aurora australis.
Right.
Are they equal?
No. Well, obviously the population density is lower, and I don't think the oval for that aurora goes much beyond Antarctica. And I don't know for sure, but I do think the northern hemisphere one is brighter. But I think that's because of the way the magnetic field lines work. So, and now I can't remember if they come out of the North Pole and go toward the south or the opposite. But it has to do with the electrons. So the polarity, basically electrons are negatively charged, and so they want to follow the field lines along the positive axis. So I guess positive is going in at the North Pole. Don't quote me on that. Anyway, but it's easier for electrons because they're lighter particles, they're faster moving, they have more energy. It's easier for them to track onto the North Pole than it is for them to track along the South Pole. So you get heavier particles, basically the positively charged atoms, basically going that way, and you don't get as many. So because they're heavier, so it's harder to trap them.
Thank you.
Yep.
So it looks like we're close to 8 o'clock, but we have time for one question here.
What would solar flares do to solar panels?
I don't know. Probably nothing. I don't know. I'm not really sure because I don't know exactly how they work. Well, I mean, basically what's happening is photons, so photons are impacting these cells and knocking electrons loose in these cells, and then those electrons move to a different place, and then that movement creates electricity. So, I mean, it's basically all light-based, so the solar flare wouldn't really do anything light-based, but, you know, if there's a lot of electrical activity in there, I don't know. I mean, if you have, like, really crappy wiring in it, maybe it'll fry the wiring, but I don't know. To be honest, I don't know what would happen. Yeah.
So, okay, there's always that last question of what you want people to leave thinking about tonight.
Oh, right.
Knowing or...
So, well, a good one is I just want you coming away from this thinking, you know, being more aware of the sun, right? So the sun is not just some static ball in the sky, right? It actually has, you know, seasons to it, right? 11-year seasons. It has a lot of, you know, it has, you know, seasons of activity and seasons of not activity. It's a dynamic object. It's not just this glowing ball in the sky, right, that gives us light and heat. There's actually a lot going on there that, you know, and that you can see if you look closely. You know, if you actually pay attention to it, you're actually able to see what's going on. So, yeah, it's fun.
That's wonderful. And you guys had great questions. So let's give a hand. Patrick?
Thanks.
Yay. Thank you. That was wonderful. And so that's tonight's program. And next week we're going to be talking about synthetic biology. And then after that we have trivia. So all you science trivia people, you know, keep studying. There's always a chance you'll win. And thanks for coming. It's a wonderful program. Thanks.